So, good morning.
Good morning.
Welcome to today's class. I want you to take you through an electric DC generator for today's class. So, feel welcome as we start our class. So, we're still on the topic of power generation. Now, today we have to go through an electric DC generator. Therefore, for today's class, the specific learner's objectives is that by the end of this lesson, the learner should be able to state Faraday's law of electromagnetic. Number 2, explain the working principle of DC generators. And the final one is identify 5 key parts in a DC generator. So this is on 8 July 2021. So now let us start with the first objective of today's class. So I want us to look down and first I would like to ask you, have you ever wondered how we convert mechanical energy into electrical energy? Yes? You got an idea? Yes, can you tell us, have you ever wondered and what did you get from that point?
Just a conductor cutting the magnetic field was causing an induced EMF in the conductor.
Yes, exactly. And whatever you say brings us to what I want us to look at. So, from the picture or from the diagram you can see here, this is a circuit of an electric DC generator. And so, I want us first to state the Faraday's law of motion. And he has said something relating to a conductor when it rotates in a magnetic field where an EMF is induced in the conductor. So, Faraday's law of motion, it states that when a conductor is rotated in a magnetic field, an electromotive force is induced in the conductor circuit if closed where electric current flows. So, when a conductor, I want you to understand, when a conductor rotates in a magnetic field, you see? So, an electromotive force is induced in the conductor circuit if closed where electric current flows. So, I hope you got that. I want us first to go through what is a DC generator. So, a DC generator is an electrical machine that converts mechanical energy into direct current electricity. Therefore, it works based on Faraday's law of induction. Whatever you have just said from the previous slide, we have said that Faraday's law of electromagnetic induction states that when a conductor is rotated in a magnetic field, an EMF is induced in the conducting circuit, which is closed, therefore electricity or electric current flows. So we have to understand that a DC generator works based on Faraday's law of electromagnetic induction. So in the process, we have said that a conductor cuts through the magnetic field lines, inducing an electric current. The output current is unidirectional or DC, unlike in AC generators. So, for the common sources of the mechanical energy that we use to rotate the conductor in the magnetic field. So, common sources of mechanical energy that we would use include diesel engines, we have the turbines, and the cranks. So, we still continue and look more about the DC generators. So, DC generators are ideal for use in battery charging. We also use them in plating, you remember that in chemistry. We also use them in welding. You know, all these are the uses of electricity. Really? So we also use them in portable power systems, like the battery, the power banks that we use in our phones, all of them. So they are also useful in educational labs and the lower power industry. So in the labs, when you go to the lab, the technician will take you through the DC generators. So we also use them in education labs. So let us move to the next objective. Now, the working principle operation. The working principle operation. So, how a DC generator works. So, up to this point, if you are asked a question, can you be able to try to explain how a DC generator works? Can you be able to this?
Yes.
Yes, you can try.
So, based on Faraday's law, when the conductor or the armature coil rotates within a magnetic field,
yes,
a voltage is induced in it. Yes.
That's correct. So, yes, just when a conductor or the armature coil rotates within the magnetic field, a voltage is induced in it. So, the direction of the induced current follows the Fleming's right hand rule. From the previous class, we learned about the Fleming's right hand rule. So we put the right hand rule, and then the thumb directs shows the direction of the conductor. So the index finger shows the direction of the magnetic field lines, and the middle finger shows the direction of the current, the electric current in the circuit. So the commutator rectifies the alternating induced current. So we go back to the diagram and you will see a part or a component that is called the commutator. It rectifies the alternating induced current to DC generator. Because generally when we are generating electricity, it is usually generated in AC. But for such a case where we need a DC, a direct current, we use a commutator to rectify the alternating induced, the alternating current into direct current. Good. So, I want us to conclude from the working principle. So, the magnetic induced EMF, the amount of EMF, depends on, number one, the strength of the magnetic field. The strength of magnetic field. So, what do you expect when the strength of the magnetic field is high? What do you expect? Will you try? Yes.
The magnitude of the induced EMF will be high.
Yes. When let us look at the factors affecting the amount of EMF. So we have said that the strength of the magnetic field. So what happens with the strength of the magnetic field is increased? We have seen that the amount of the EMF will increase. So the other factor is the number of armature conductors. There are some that have more than two, others have one. So the other part is the continuous rotation results in continuous generation of electricity. So the external mechanical input, like an engine, keeps the shaft rotating. So we have just looked at the common sources of the mechanical energy that we would rely on when rotating the armature or the conductor. Yeah. So let us look at the key components in our diagram. So what are some of the key components that you can see? Yes. We just look with your eyes, you see, you name. Yes. Yes, you have the commutator. So observe and see.
Conductor.
Yes, the conductor. Another person. Yes. What do you see? Eh? Yes, we have the conductor wire.
Magnets.
Yes, the magnets. We have the magnets. Another one. I want us to read at least 5. Yes. Good. The carbon branches. The last one.
You have the graph showing.
Okay, I want us to know, just exclude the graphs. This one is for showing you how the EMF produce flows. Yes. Just observe. You have the magnets, you have the commutator, you have the carbon brushes. How do you call this? The load. Right? Yes, you have the load. There's something else I want us. Yes? No, that's not a part. That's not a part. It's this part here, inside. You have seen what? The one that rotates in the magnetic field. The armature. Yes, the armature. Now, briefly, let's look at the functions of those parts. So, the commutator. The commutator, we say that it is used to rectify the alternating current into DC current. Okay. So the carbon brushes, they are made of carbon or graphite. They maintain the electrical contact between the commutator and the external circuit. So the carbon brushes, they maintain the contact between the commutator and the external circuit. This is the external circuit. You see this line? Then you have the commutator. So they maintain contact between the commutator and the external circuit. So we have the magnets. This is simple. They just provide the magnetic field. So the conductor, it carries the generated electric current. So we are winding up. Yes. So for today, I came up with a video here for better understanding. Kindly watch it keenly for you to understand it.
Welcome to our exploration of DC generators. Today, we'll dive deep into the components that make up these fascinating machines and how they work together to generate electricity. At the core of every DC generator is the armature, a coil of wire that rotates within a magnetic field created by stationary magnets or electromagnets. As the armature spins, it cuts through the magnetic lines of flux, inducing an electromotive force EMF in the coil. This induced current flows through the armature windings and is collected by stationary contacts called brushes. The brushes are in contact with a split ring commutator, which consists of 2 segments, known as the commutator segments. When the armature coil reaches a 90-degree angle, the change in magnetic flux induces the maximum EMF, resulting in a peak current flow. As the armature continues to rotate to 180 degrees, the induced EMF drops to 0. At this point, the commutator segments switch the connection of the brushes, ensuring that the current flows in one direction. This design ensures a steady flow of direct current, DC, from the generator, which can then be used to power various devices and systems.
Good. That's the end of the video. So thank you for attending the class and listening